In this question we are given a cylindrical barrel with a diameter of 2 feet, which means that the radius is 1 foot, and it contains water, rainwater, and the water is draining through a valve not shown here, somewhere at the bottom of the barrel. And the rate of change of height is given by the function dh over dt is equal to this expression. H is measured in feet and t is in second. And so we're also given that volume is pi r squared times h. We need to find the rate of change of volume, notice volume not height, of water when the height of the water is 4 feet. So first we need to use this formula here. So volume is equal to pi r squared h. And so as we said, r is equal to 1 foot. So this is equal to plugging in 1 instead of r equals to pi h. Differentiating with respect to time gives us dv over dt is equal to pi and then dh over dt. So we need to find, once we find what is dh over dt at a time when h equals to 4, we can plug in this number here and we will find the change in volume at the time when the height of the water is 4. And so to find this, we just plug in h equals to 4 in this expression. It's negative 1 over 10 times square root of 4, which is negative 2 over 10, which is negative 1 over 5. So plugging negative 1 over 5 back in here gives us negative pi over 5. And the units are cubic feet per second. So this is the rate of change of volume. It's cubic feet per second. And so this is our final answer. In this question we are being asked whether the rate of change of the height of the water is increasing or decreasing at a time when the height of the water is 3 feet. And so let's find for that the derivative of the rate of change with respect to time. So we need to find the d to h with respect to dt squared, which is the derivative of dh over dt. But notice here that dh over dt is a function of h, so it's not a function of t. So we need to use the chain rule here, and we first differentiate this expression with respect to h, d over dh of dh over dt, and then we differentiate multiple times dh over dt, the variable here, so dh over dt. And notice here that these two functions are the same, but they just happen to be the same. This function is always dh over dt, and this function is usually f of h. It just happens that f of h is dh over dt, so don't get confused that these two are the same. So let's differentiate this expression with respect to h. This gives us negative 1 over 20 times square root of h times dh over dt, negative 1 over 10 square root of h. Square root of h cancels out here. They look like n in my handwriting, but these are h. And then negative and negative, so it's positive 1 over 200. And so we can see that the rate of change of the height is increasing because the derivative of it is positive, greater than 0. So it is increasing. So in this part of the question, we are given the initial condition that at time 0 the height of the water is 5 feet, and then we are being asked to use separation of variables to actually solve for h in terms of t. So let's separate the variables, bring all t's to the right hand side and all h's to the left hand side, and we'll get dh over square root of h is equal to negative 1 over 10 dt. Integrate both sides, you get integral dh over square root of h equals integral negative 110 dt. Integrating this side gives us 2 square root of h, and this is equal to negative 110t plus a constant. Don't forget the constant because we have the initial condition to find what the constant is. Plugging in the values for the initial condition, h is equal to 5, so 2 square root of 5 equals t equals 0, so this is 0 plus c. So we found that c is equal to 2 square root of 5. And so then, plugging it back in, we get, let's write it here, we get 2 square root of h equals t over 10, negative t over 10, plus 2 square root of 5. Divide by 2 and then square the right hand side. When we divide by 2 we get h equals negative t over 20 plus square root of 5 squared. And so this is our answer for h as a function of t. Thank you, and I will see you in the next video.